Hello and welcome to this Edexcel A-Level Geography Enquiry Question Review. And this session is looking at Carbon Enquiry Question 1. How does the global carbon cycle operate to maintain planetary health? So as always, first thing we do, let's check the specification. And again, it's important to check the specification because it tells us of all of the key terms that you will see in the exam questions and the key terms you'd be expected to use within your answers. It also shows you the key information that you will need to give from the answers. So often in geography, there could be other information out there, but it's important to focus on the content in the specification and what it wants you to know. The explain questions will tend to relate to just one or two of these detailed content sections within a key idea, whereas the assess and evaluate questions are likely to look at a number of the different key ideas linked together and different sections of the detailed content within them. So having a look at the key ideas then. So what we can see is that there are four main stores of carbon in the carbon cycle, and it operates as a system, as the same way as coasts and the water cycle. In the global system, is a closed system with everything flowing and being stored or sinks in between them. But then each of these individual systems like geological, atmosphere, biosphere and hydrosphere all act as open systems because the carbon can move and have inputs be transferred through it and then also have outputs into the other elements of the system. So one thing to remember is that we talk about petagrams of carbon, and petagrams is 1 billion tons effectively. Also the same as a gigaton, okay, and that will be referred to within the question. Other key terms to know are sequestration, which is the long-term storage and capture of the carbon. A carbon store is where there is a large amount of carbon held within it, and a carbon sink, which means that it removes or stores more carbon than it emits. So let's have a look at each of the individual sections. So first of all, we have the geological store. This is the largest by far. It is absolutely huge and makes all the other stores pale into insignificance. It's absolutely massive. Now, the residence time, the carbon is stored within this for millions and millions and millions of years. And it can take a very long time for the carbon to move within it. And basically what has happened is all the dead plants and animals which have died and decomposed can then get turned into sedimentary rocks such as limestone, chalk, shale, or if there is a lack of sort of oxygen present, they may turn into the key fossil fuels, oils and gases. And so this is where much of the geological carbon is stored. Now, this geological carbon, it can be locked in, or it can gain more carbon, particularly through the process of weathering. As the carbon dioxide in the air dissolves in the rainwater, turning it slightly acidic, which can lead to weathering of rocks. And then this sediment and material can then get moved down under the oceans and under lakes, and over millions of years can turn back into sedimentary rock. So becoming a sequester and a sink of carbon. The carbon can be released naturally by volcanic outgassing. So this is where you have subduction zones and the oceanic plate is subducted underneath it. The rock is then melted and the gases within it are then released at volcanic eruptions. Now, on some occasions, the weathering of the rock can also release some of the carbon into the atmosphere as well. But overall, it is believed that more weathering leads to more water being stored in geological than is being released into the atmospheric. Moving on, we look at the atmospheric. Now this is the smallest of all stores, 750 petagrams of carbon. It is completely tiny, particularly when compared to the geological store. And there are a number of ways in which carbon can be inputted or could be outputted out of the carbon system. But it's important to remember that carbon is a natural gas within the atmosphere. It's always been there. And carbon dioxide is a very important greenhouse gas. It keeps the planet habitable. Without the greenhouse effect, then the planet would be too cold for any sort of life. And by looking at ice cores and other data going back over hundreds of thousands of years, we can see the past range of carbon was anywhere between 200 and below 400 parts per million. Now this becomes an important figure, because what we'll see with human action is that we are far exceeding the past range of carbon dioxide in the atmosphere. When we get too much carbon dioxide, this can reflect too much heat energy from the Earth, which can lead to the enhanced greenhouse effect, which is then leading to climate change. So that's the sort of the main store within it, held within the air. Now, the carbon can get there through volcanic outgassing from the geological store. But we can also see that by combustion of plants and by decay and decomposition of plants, that can release carbon into the atmosphere. We can also see that as we get warmer oceans, the oceans can contain less of the carbon, and with increased levels of storms, this can lead to more carbon being released into the atmosphere as well. But it is important to realize that the biggest contributor to atmospheric carbon is now human action in the action of burning fossil fuels or burning plants for combustion, for heat and for fuel. The outputs generally relate to photosynthesis of plants into the biosphere, or photosynthesis of plankton, which then goes into the hydrosphere. So if we look at the biosphere, this is 4 times bigger than the atmospheric store, and a big part of that is soil. It's very important that soil plays a key role in storing carbon. Now, the input is often photosynthesis through the plants, taking the carbon from the air and using sunlight, and this leads to the net primary productivity. So this then will depend on things like climate, diurnal changes, day and night, the seasons, soil health and land use. The greater the level of net primary productivity or biomass, which is the plant life and litter or leaves that are produced, then the healthier the ecosystem. This will lead to more food into the food chains and will lead to nutrient cycling. Again, animals can take in a lot of the carbon from the food, but they can also output it through respiration or breathing. And when they die, they can also decompose, which then releases some of the carbon into it. But often what happens is with the decomposition, with the bacteria and with the animal dung, and also the decomposition of plants, this can lead to carbon being stored into the soil. And as we can see, the soil is twice as big as the atmospheric store. And it can be stored in a number of different ways, either in the humus layer, the litter and leaf mold and decay layer on the top of the soil. It can also be held in peat bands or peatlands and peat bogs, where the rich plant matter decomposes with reduced oxygen, so it makes it very rich store of carbon. Wetlands are also a very important store. And also very much of the carbon is stored within permafrost and the cryosphere, although the actual levels of this are unknown. Now, with a lot of carbon in the soil, this is important for soil health, which then is very important for nutrient cycling, which can have an impact on net primary productivity, which can have an impact on there. So if we destroy the soil health and net primary productivity and the animals through climate change or agricultural processes, this will have a big impact on the whole of the system. By looking at negatively affecting the ecosystems, it will lead to yet more carbon dioxide being released into the atmosphere. Then we have the hydrosphere. This is the water or the ocean carbon cycle. Now, the major input to this is through photosynthesis and phytoplankton, which is the net primary producer of the ocean hydrosphere. And this then gets into the food chain. Now, over time, you can have the biological pump. And this means that as the plants and animals start to decompose, they fall to the bottom of the seabed, can become depressed, and either stored in the deep, dense water or can be turned into the geological store. And the deeper, colder water hold a massive store of the carbon dioxide there. Now, this gets circulated through the hydrosphere through the physical pump. And a major part of the physical pump is the thermohaline circulation. This is the movement of currents around the world, driven by heat and by the climate and wind cycles. Now, what we tend to find is that there are areas of upwelling, and this can contain lots of carbon-rich water, and this can lead to very healthy conditions for plant and animal life. We also have downwelling as well, where the water is drawn down to replace the water that's been upwelled and then is moved around by thermohaline circulation. So this is a key process in moving carbon around the hydrosphere. Now, the major concern with the hydrosphere is as the oceans have continually warmed, they can hold less carbon dioxide. And that merged with climate change leading to greater storms and greater disruption in the sea surface is going to see a much greater level of carbon from the hydrosphere moving back up into the atmosphere. Okay, and these can start to form parts of feedback mechanisms, which we'll discuss later on. Finally, then we have sort of the overview of the human activity. Now, over the last 200 to 300 years, with increasing population, with increasing economic development and the reliance on fossil fuels for this growth, then this has seen a massive change from carbon stored from the geological sink into the atmosphere, mainly through the combustion of fossil fuels and farming practices. And this, as we've said before, is leading to the enhanced greenhouse effect, which is leading to climate change. This climate change, as we've already said, leads to warmer oceans and more storms, which again can lead to more CO2 in the atmosphere. These changes to climate can also have an impact on the net primary productivity and soil health. This could lead to the degradation of ecosystems, which are a major sequester of the carbon, and this, along with the increased bushfires and combustion of plant life, will also see a greater level of carbon into the atmosphere. So we can start to see that we're fueling this positive feedback mechanism with things leading to more and more atmospheric carbon. And changes to land use can reduce net primary productivity and soil health, which again impacts on the ecosystem and the ability of the ecosystem to sequester carbon. Things such as tilling the soil or ploughing the soil can reduce the level of carbon within it. That can lead to increased leaching from changes to rain patterns and increased flooding and droughts. And again, this can help to release more carbon. So you can start to see how the carbon cycle is also very much linked to the water cycle because of the links to climate. In summary then, we can see it is a very detailed and complicated system. We have the inputs to the individual stores, but it acts as one closed system. And there are different ways in which carbon dioxide can move between the different stores. But the main concern that we have at the moment is how do we reduce the amount that is going into the atmospheric store, and how can we lock it into the other stores, ideally into the biosphere or the geological store. Thank you very much for watching. I hope that's been of use. Hopefully see you again soon. Bye.